Hope so.
Okay, so our last speaker of the morning is Svante Janson.
Hey. And this too is joint work with Alan Sokol and with previous speaker Alex Scott. It was something we discussed a few years ago, but then we never completed or at least wrote anything up. And so now I thought it would be a good opportunity to try to resurrect it now during this program here.
Try to force your two co-authors to actually work on it.
Well, also to try myself to actually work on it. So first of all, I should say that although I'm a probabilist, there's not going to be any probability at all in this talk, which is a little bit unusual for me, but it has happened before. Secondly, that this is really quite elementary analysis only, no fancy deep theorems, unfortunately. So what it really is that we set out to study a simple example of this phenomenon of locating zeros in the complex plane and see how they somehow converge. So we wanted to look at a simple case where one could do things more or less explicitly. So it doesn't have any obvious important physical application or even meaning. So let me begin over here maybe. So we all know how to compute this sum from k to n of n choose k times z to k. But suppose now that we take only a partial sum here. So let me define fnr, meaning that we go from up to the rth term. Oops, x, well maybe let's keep it z. So this is clearly a polynomial in z, so it has r roots and so on. And the idea now is to study this as n goes to infinity and r is like a constant. Of course, r should be between 0 and n, but let's be more specific and say that r is roughly alpha times n, where alpha is a constant between 0 and 1. And we can also look at the complementary sum, which is the sum from k equal to r plus 1 to n, choose k of z to k, which is 1 plus z to the n minus f n r z, obviously. Also by usual symmetry here, this is sent to just f with indices slightly changed. I think I'll look here to at least reduce the probability of getting it wrong. If you take f, instead take n. So here we have n minus r. You have r plus 1 terms here. Here you have n minus r. So if you take n minus r minus 1, you have the right number of terms, and then you replace z by 1 over z to get the upper tail. So we have 1 over z here, and then we have a factor z to the n in front. So it's and of course here the ratio now goes to 1 over alpha instead. 1 minus alpha, sorry. So of course it's equivalent to study these two, but it's natural to also to study them together because of this. And say the main result is we have a picture in the plane something like this. For each given alpha, we have a curve which looks something like this. This we can call gamma, so gammas of alpha. It should be more symmetric. It should obviously be symmetric about the x-axis. My oldest daughter tells me that I ought to use PowerPoint in my lectures, and maybe this is one reason why. But on the other hand, I must tell you that yesterday I checked how this curve looks by doing a plot on Maple, and it came out even worse than this, actually. It wasn't even connected around here. But if you, like me, prefer analysis, you can have an exact formula. This is the curve where you have a certain constant C alpha times absolute value of z to the alpha equals 1 plus z. And here this C alpha is just some number 1 over alpha to the alpha 1 minus alpha, which you are used to getting when you do Stirling's formula and binomial coefficient. Maybe the important thing is that this C alpha is such that the curve passes through a point here, which is just alpha over 1 minus alpha. Okay, we'll see later why this comes out, or perhaps not later. And the asymptotics here is that, let's see now, I try to write it on this, let's go in this picture. So if we look at the, see to get it correct now, in the interior part, this region here, here f and r is asymptotic now, just like 1 plus z to the n. Well, first of all, that's not surprising. So we have 0 is somewhere inside here, like this. Well, that's not surprising. When z is small, it means that first terms are important ones. So at least, so if r is, I mean, if z is small now compared to alpha, we have captured almost everything. So that's what we would expect for. Certainly we have it close to the origin, and it actually is true in this region. If we go outside, on the other hand, it turns out that f is dominated by the last term. Well, that's also not surprising if z is very large. Certainly these terms will just be increasing, and I'll look at that let's look at that in somewhat more detail. Let's call this term ak, and let's see what the ratio is. Ak over ak minus 1. Well, we get the z here, and then from binomial coefficients we get, see now to get it correct, okay, we divide by another k and get an n minus k plus 1. So if, in particular, if k is like r, which is alpha n, this is roughly 1 minus alpha over alpha times z. So you see here at this point the large terms are about the same, which means that we are roughly about maximum. And you could I said there wouldn't be any probability in here, but actually if you let z be positive, you can think of this as a binomial probabilities, except for scaling factor. I mean, if you divide by this thing, you have the binomial distribution with probability z over 1 plus z. And then it's well known where the maximum is that, and you have a, of course, close to maximum, these are more or less constant. And that's exactly what happens in that case. But we also see that if z is substantially, well, if z is larger, say that the absolute value of this is greater than 1, of course, then these increase geometrically. So if z is large, this will dominate by the last term, the rth term here. And you can more precisely sum ones close to r, approximate them by geometric series. So you will have a very precise result in this region, which is like f of f z is like z over z minus alpha 1 minus alpha. Not that it's very important, and but let me just show you how precise you get. This is something which you obviously get from Stirling's formula, this factor, but then we have constant CR. This is this C, the same C I had here at evaluate point r over n, which is roughly alpha times z to r over n raised to power n. Well, this is just z to the r, but since I want to look at asymptotics, this is looks nicer. So
is that for the interior region or the exterior region?
It's actually in both these regions. That's well, I didn't really intend to write across, but I want to emphasize that it's in both these parts. So here we have the green boundary between these two regions for f. Whereas for G, we have instead the outer boundary here, which distinguishes two faces which are very similar. So in this case, when Z is large, we capture almost everything. So here, G is like 1 plus Z to the n, and inside, so in both these regions, we have, well, G of Z is almost exactly the same thing as this. It is, or to be more precise, it's exactly minus this thing up here. And it's not surprising that it is minus that if you look at the sizes of the things, because it turns out, of course, we have to have some kind of continuity here. We'll also have some kind of discontinuities at the boundary, but some kind of continuity at least. And it's not so it's not surprising. The boundary is exactly when if you take absolute values here and put that equal to absolute value of the leading term there, they will be the same. So you can put that more precisely by looking at the logarithm of the absolute value and divide by n. And here it will converge to logarithm of 1 plus z. And in these two, it will converge to log c alpha plus alpha times log absolute value of z. And similar with f, we'll have in these two regions, f will converge to the same thing. Let me try to emphasize that in this way. Log c alpha plus alpha log z. But here we will get convergence to logarithm of 1 plus z. So I should say now that these convergences convergences here and asymptotics here, they are, of course, should be uniform in any compact subset in these regions. So if we take a compact subset here or a compact subset there, we have convergence to corresponding things. But we'll have singularities at the boundary, which of course is the point of doing all this. But you see that this boundary curve is exactly where these two asymptotical functions coincide. And the same thing here. And now I'll explain soon why we get this type of behavior, but let's first note that, or if we compare these two limit functions, this one which we have here or for f inside, or this one which just logarithm of z, it turns out that you just check that this one is the larger one in the intermediate region, but the log 1 plus z is the largest one here and there. So if we go back to this thing, do you remember that we said that say we are in the interior here, so in that region f is essentially just 1 plus z to the n, so nothing strange with the asymptotics of f. And on the other hand, g is very small, just the tail here, which is very small and dominated by its first term, so that's why we have this limit for g inside here. And outside here we have the opposite. G is everything and f is quite small and has this limit. So somewhat more interesting perhaps is the intermediate region, where now both of them are dominated by the last term there and first term there, which are essentially the same. But these terms are now much larger than the total sum of them. So we have that's of course because we have massive cancellations here in this sum. And note in particular that this intermediate region does not contain any positive real number. So that's why we can have cancellation, and we do have. So the sum of f and g is much smaller than any of them. And that of course means that implies what said that g is asymptotically equal to minus same as f. Of course the sum of them, as I said, is very small. Now before explaining, well, I think yes, I can explain a little how this is. Well, first of all, I should say, as some of you already know, the fact that we then have a discontinuity limit here, well, limit is continuous, but certainly it's not analytic here. It means that we necessarily have zeros of g accumulating to this red curve and of f accumulating to this green curve. And for those of you who are not familiar with the argument, let me just repeat quickly. The idea is that suppose that we had a small region here without any zeros of g for large n, or well, even for subsequence when n goes to infinity. Well, in that case, logarithm of g would be a nice harmonic function. Logarithm of absolute value of g. I mean, logarithm of g is analytics. Logarithm of absolute value of g is a nice harmonic function in this region, and it's easily shown to be bounded above, well, when we divide by n. So by usual analysis, I mean, it's form of well, usually talk about normal families for analytic functions, but theory works for harmonic functions too. So it would have to converge uniformly on smaller disk to a harmonic function. Well, but on the other hand, we know that the limit is this in the outside part, and it's this in the inside part, and of course they don't combine to a single harmonic function in this disk here. So the conclusion is that there must be complex zeros, of course complex, must be zeros of g which accumulate to every point on the red curve, and zeros of f that accumulate to every point on the green curve. And you can even tell what the asymptotic density of these zeros are by simple analysis. It will be given by the jump in the derivative, in the normal derivative of this limit function. Compare the derivative in that direction and that direction here. But on the other hand, of course, this tells us that there are no asymptotic no zeros anywhere else. If you take any other region in the plane, if n is large enough, there will not be any zeros of f nor of g there. Well, how do you prove such a thing? The idea is, back to what this calculation I did here, and I said that if z is small enough, more precisely if the absolute value of this is strictly less than 1, then certainly this will be like a geometric series with so if well, say the opposite perhaps, if z is if this is absolute value is bigger than 1, this will be like a geometric series where terms increase, and this is certainly dominated by the largest term, and if you estimate it to closer, you'll have a correction factor like this summing a geometric series. You have to be some more careful than what I'm saying now, and in particular I really want to do that also when the absolute value here is equal to 1, and then you have to be more careful and do analysis more precisely, but it is possible to estimate this sum and see that it really is, or in spite of the fact that we have lots of cancellation going on, it is given by this factor times the largest sum and the large term. You estimate the largest term using Stirling's formula, it gives you this. So now no more color. So let me draw a circle in this picture. This is supposed to be a circle. Absolute value of z is alpha over 1 minus alpha. So this circle will pass through the middle of this middle region. Point is that outside this circle, as I said, it's easy to estimate f, and it's given asymptotic by this formula. And as I now that might you, and inside it, for the same reason, you do the same thing with g. And g is given by this red formula here, asymptotically. Well, that might lead you to believe that there is some phase transitions going on, and therefore some zeros also on this circle here. But that's not the case. And to see that, as I said, we can do this argument actually also on this circle. Now let's look at f. So outside.
Why should we think that there are zeros there?
Well, because well, maybe you're more clever and see that there are no no problem going on. But since we have to do the, this series will behave differently inside and outside this circle, you may think that something goes on there. At least it's not impossible. But what actually happens is that if we are, say, outside or on this circle, as I said, f is dominated by the largest term, we have this asymptotic. Now suppose we are inside. Well, then it's not so easy to estimate f perhaps, but we can estimate g by exactly the same method, and that gives us exactly the same thing except for a minus sign. But then we also know that in that region, as I said, the asymptotic here, this term, is much larger than 1 plus z over n, which is the sum of them. So f is asymptotically the same as minus g. And therefore, in this region, say inside here, outside this green curve, when things change, the asymptotics for g gives us asymptotics for f, which match up perfectly with the asymptotic we had outside the circle. So there really is no discontinuity of any kind at this circle. It's just that we have to do the argument in two different ways. But we get the same result. It fits smoothly. Everything is analytic. But that also tells us what happens down here at the green curve, because again we look at this is all inside the circle here. So this is the region where we can estimate g by its largest term. And therefore we use this formula here to estimate f as, well, as 1 plus z to the n minus g. And it's just a question of which term of these two is the largest one. I just talked about the case when g was much larger than this, but inside the green curve here, it's the opposite thing. The g term is smaller than 1 plus z to the n, so this dominates, and we get the result. And of course, conversely for g outside. So everything comes from direct estimations here. You used, of course, Stirling's formula, and you have to said to be rather precise with the estimates when absolute value is equal to 1. So let me finish by saying something. I said that this was just some polynomials we wrote down. Of course, one could do things explicitly.
Svante, before you go on, can I
Yes?
just ask you one question? Since you have to treat a little bit differently what's going on the circle
Yes.
versus outside, but nevertheless you want that these convergences are uniform on compact subsets of
Yes.
domain.
Yes. The point. So, as I one has to be careful. So to formulate more precisely, I can the argument using this approximation with the geometric series actually is if we do it for g, which is inside this circle, it works uniformly inside the closed circle minus any small neighborhood of this point here. But that, of course, is a very important technical point, that we can do it not just in the open but closed circle, we can do it uniformly. One can do exactly the same thing with exactly analogous results, and a picture which looks like this but a different formula. Also, if you take the exponential series and let's do it like this, sum from k equal to 0 to r, and r is like a constant. In that case, alpha is, of course, could be any positive number. Take r equal to n, for example. So I just say similar, and you could look at the complementary, the tail part there too. But let me finish with another thing which combines the two topics in the title of this program, combinatorics and statistical mechanics. Namely, I said this had perhaps no obvious statistical background, but let's look at something which is some combinatorial statistical physics intersection here. We take the well, I had h before. This is another h. H and r. The sum of n choose k. Now we take all the way up to n of let's say z to the k q to minus the minimum of k and r. Well, we can interpret this is the partition function for the cluster model on a uniform matroid of rank R. Well, if you know enough of matroid theory, and especially if you were here last week, you heard a lot about matroid theory, then you should see why this q to minus, this is the rank of a set of k elements, corresponds to usual q to plus the number of components in a cluster model on a graph. And if you don't know matroid theory, you prefer just to look at this as a definition. And now we can, of course, we split the sum into sum from k to r and r to infinity, or r plus 1 to infinity, and we see that this is exactly f n r of z divided by q. So q is some positive real number here. Thus q to minus r g n r of z. So now we can ask what happens with this as, again, r, n goes to infinity and r is like a constant, alpha times n, and q is a fixed number. Well, we have here z over q, which means that if I redraw my picture, so for the g part, we still have the red boundary here, which is where we have the discontinuity, or discontinuity at least in the derivative. But for f now we have z over q, so we have to scale this. Suppose q is larger than 1 but not too much larger, then the inner green curve will blow up like this, and we still have 0 somewhere here. So now we have this will be q times alpha over 1 minus alpha, whereas this again still is my alpha over 1 minus alpha. So now we have different asymptotics for f inside and outside the green curve, and for g inside and outside the red curve. So we get 4 different regions, and if I find my notes here, well, let me just call them. Well, so it turns out that here it is the f part which is largest one. So the asymptotics now of 1 over n logarithm of h absolute value is like this. Here we have logarithm of 1 plus z over q. And in this region here, both of them are, this is the region where both of them are same, the largest term, and it turns out they will fortunately not cancel, and we have same term asymptotics again, log z over q. Outside again it is the g term which dominates, which gives us logarithm of 1 plus z, and then we have this q to minus r, which ends up like this in the asymptotics.
Log q.
Log q, yes. But then we have the fourth part here, which is inside now the green one when it's expanded, and outside red one. And then it turns out, well, as you can see by, I said that here f part dominates by continuity, that has to be largest here too. But here the g part dominates, so g part is largest here. So actually there will be another curve in between. When one of, so, and we will, it turns out that this formula actually extends all the way out here. So this really is not a phase transition in the limit here, and this one too. So in the limit we have these 3 domains. This actually is part of a circle because you have to compare, it's when this is equal to that. So it's which is just given by circle if you do mathematics here. So we have these three regions, and we get different limits. And again, we have therefore necessarily zeros in the complex plane that accumulate to this curve here, these branches. And you see that on the positive real line we have one intersection here, so we have one phase transition there and nowhere else. Okay. Oh, any questions, or does everyone prefer to have lunch? Okay.
Did you get to it from the cluster model or did you do it the other way around?
Well, no, I mean,
Why did you attack this problem?
Well, actually, I think it was one of my co-authors had the idea, but I said I think the main idea was just to have something simple to start with, and then it was an observation that one could think of it in this way. But I don't think this was the primary motive.
Yeah, it was my motivation. This is the independent set polynomial for the uniform matroid.
Oh yes, that's right. I forgot
And
that.
then this is the two-variable tuck polynomial for
Yes.
the uniform matroid. So it is a simple example of phase transitions in the tuck polynomial, but for a family of matroids.
Okay.
Okay, let's thank our speaker.